Okay, hello. So today we're going to be presenting TACO, which is Text Adaptive Compression. And I'm Robin.
I'm Lucas.
And I'm Chen.
Yes. So a little bit about this compression. So what is it? Basically, traditional image compression techniques you guys have already heard of. So PNG, which is a lossless based one, and JPEG, which is more of a lossy based one. Basically, we have our original image. We can send it through one of these image codecs, and we can get some relatively high compression ratios, which is good when we want to transfer files and stuff, and so forth. But can we even do even better, like 25 to 1, 30 to 1, or even 50 to 1? Like, can we get 50x savings? So actually, that's possible with neural network based image compression techniques. So traditionally, this is done with autoencoders. So given some inputs, we have some encoder learning some latent representation of it and decoding, therefore reconstructing the output. Uh, Other methods of doing this is by using GANs or diffusion-based methods or training end-to-end networks to learn this representation. So what is Taco? What is our thing? So our thing is basically an encoder-decoder network that also utilizes text captions in addition to the image to create a reconstruction of the image. So if we just look at it from a high-level view, in goes this tricolored, fluffy Pomeranian dog. It becomes this latent representation, which we call Y, and then it goes to this decoder to become this reconstruction of this output. So somewhere along the lines, this text caption also goes in, but I'll go into more detail with it in a little bit. So what is encoder actually? So the authors of the original paper complicate this encoder. Basically, they add a bunch of convolution blocks to find different spatial resolutions, and they also add residual blocks or residual connections and attention layers within this mechanism for that added complexity and also higher complexity latent representation Y. So they do something similar for this decoder part as well, which I'll uncover right now. And this hyperprior stuff you don't have to worry about right now, but you can look in more detail about it in the paper itself. What we really care about is the authors have a really complicated encoder-decoder architecture. Additionally, they process text captions with something they call a text adapter. And basically what that is also something very similar to this encoder. Basically, they use a pre-trained clip encoder along with many more deep neural network layers, and they relate it back to the image with cross-attention layers uh, to make a more efficient, more complex latent representation Y that we want to know more in the future. So adding this all together, our reconstructed image output is better than just using an encoder decoder. So how do we improve on this? One, the authors basically had very short captions, so maybe increasing contextual information will help. Secondly, improving the attention layer performance. And third, maybe improving the clip model or the pre-trained clip encoder. So improving caption and word encoding in that part. So what does increasing context in these captions mean? So in the original paper, their data sets included captions such as this. So very simple, an old stone building with red stairs, dot, dot, dot. It's very short, but doesn't describe the whole picture. So with improved caption, it not only describes the scene a lot more fuller, but also finds patterns. So such as this matching red door, along with some symmetry and more complex reasoning about this image is added within the caption.
For improving the attention mechanism, as you can see from the diagram of the original model, there's 3 cross-attention layers which are used to insert the text information into the encoder. And these cross-attention mechanisms, when they use the standard attention mechanism, they have O of n squared complexity, which means that if the text adapter were scaled up to handle really long text inputs, that could become a major bottleneck and a source of computational cost. So the idea here is to replace the attention mechanisms with the linear ones described in the Lin-Former paper.
For caption and word encoding, we aim to address a limitation of clip is that it relies on image text alignment to associate word with visual concepts, and this could potentially overlooking deeper contextual meaning within the text itself. Our solutions aims to use a LLM-based keyword extraction, and in this case, we use TF, IDF, and NER for accurate or more accurate word importance modeling, thus better helping the model retain important feature while compressing the images.
For our experimental setup, we used the 3 metrics to determine the quality of the compressed and then decompressed image. These metrics are the same as the ones that were used in the original paper. And the first one, LPIPS, measures the perceptual similarity with the original image, and here a lower number is better. PSNR measures the pixel-to-pixel accuracy, and a higher number is better. And then FID measures the distribution realism, and again, a lower number is better. And the three datasets that we used were the MS COCO dataset, which is the most important one as it contains the most images, and it has 5 captions per image. Then we used for testing and validation the CLIC dataset and the Kodak dataset. For both of these, they don't come with captions, so captions were machine generated by OFA, and it's worth noting that the Kodak dataset, while small, contains PNG images, so it's lossless.
Yes, so for the first of our results, basically increasing the caption information context. So what does this mean in terms of results? So we validated this on 3 data sets, so MS COCO, the validation, click validation sets, and also Kodak validation sets. And we saw 3 basically main metrics. So LPIPs, you can kind of think of it as how well the image was reconstructed. So with this context increase, lower is better. So we're actually able to achieve a lower LPIP score in all of these metrics for these 3 data sets. Similarly for PSNR, you can think of this as like higher detail or greater detail reconstruction. We did slightly better than the initial Taco architecture in all 3 data sets. And next, on the FID, so the realism score, we did very similar to the Taco architecture with this increase. So these results are to be expected. Increasing detail would mean a greater complexity latent space. So I assume these would be how it works. And some things to think about is at some point in time, this latent space will become saturated. So it will become necessary to add more dimensions to this latent space. So that might increase some memory usage. And secondly, the benefits of this method will eventually converge, i.e. there's only so many words you can add to a caption until it eventually becomes useless noise. Yeah.
For the linear attention, you can see for the accuracy, a couple sample metrics. And generally what we saw was that the using the linear attention mechanism somewhat decreased the model's performance. It was still reasonably close to the original, but there was a definite performance impact. And meanwhile, for the time, we scaled up the inputs into the cross-attention layers to simulate an increased caption size being handled. And we found that that had no impact on the actual time that it took to do the training and the inference. So what we found was that the cross-attention mechanisms were not a significant cost of the of computational complexity, and therefore if the time that it took wanted to be improved, it would have to be improved elsewhere. Though it is worth noting that due to GPU limitations, we could only test input sizes up to about 1500, so maybe for very, very long ones it would change.
So for our experience with improved captions and word encoding, we noticed a slight increase in LPIP scored for all datasets, which suggests a minor perceptual difference in reconstructed images, but the overall quality remains competitive. Small pixel variations is also observed, with PSNR slightly decreased for COCO and Kodak and increased for Click. The less than 0.5 dB change remain within acceptable fidelity limits. FID improved for COCO, but CMMD slightly increased for Kodak, indicating a subtle height level feature shift which needs further analysis. One of our explanation for this is that short captions, which are used to test this improved caption word encoding, are used by the originals caption by the authors, and thus longer caption could provide more meaningful context and improve the compression performance. In conclusions, we generally saw some improvement in our experiments, but they are not very perfect.
Yes, so one way our experiments can be improved, for example, in contextual information, the trade-off between the caption length and also how much it affects the output of the model could be explored in further detail, along with not just exploring highly detailed captions or reasonings, but other domains of knowledge about the image itself as well.
And if we wanted to speed up the model, a linear attention mechanism could only potentially be useful for very, very long inputs. So we'd have to look elsewhere, such as using different convolutional layers or some other modification.
And for improving the caption and word encoding, to further address clips' lack of semantic reasoning, and some possible approach could be context-aware weighing instead of independent word scores, semantic role analysis for improved text-image grounding, LLM assist refinement to enhance deeper text reasoning, and hierarchical concept representation to distinguish object versus abstract themes, and also handling long captions more effectively.
Yes, and thank you. Please give us a good rating, and you'll get a taco.